All right, so let's look at the points. Look at point A, composition of atoms in terms of positive nucleus and negative charge electron. This is exactly the same as chemistry. So for point A, you are expected to know things like um, for example, proton, electrons, neutrons, relative mass. We have 1 over 1,840. Neutron is 1. Relative charge, positive, -1, and 0. And then where they are found, nucleus, nucleus, and electron shell. Okay, this will be the composition point A. It's yeah, purely chemistry. So if you look at point B, using the terms proton number and isotopes. So for for example, okay, we know the proton number is basically the number of proton in an atom. Nucleon number is the total number of proton and neutron in the nucleus. And isotopes, like in chemistry, we say they are technically atoms of the same elements with same number of protons but different number of neutrons. So with the number here, for example, let's say sodium 1123, you should be able to see proton is 11, electron is 11, and neutron is 23 minus 11, 12. See, and then another sodium atom, 1124. Then you have same thing, 11 for proton and electrons. Neutrons here will be 24 minus 11, 13. So these two, what we call sodium 23 and sodium 24, they are isotopes. Okay, this is point A and point B. So far, okay?
Yeah.
Okay, next is nuclide. Okay, so for nuclide notation, they follow this A, Z, X. On top is the nucleon number. Below is the charge. X is the particle. So for example, a proton. Okay, proton is P. The mass is 1. And the charge is +1. So it looks like this. For a neutron, is N. The mass is 1. The charge is 0. And for an electron, the charge, the mass is 0, almost nothing, and the charge is -1. That's how we represent them in what we call a nuclide notation. Okay, and what exactly this is for radiation. Technically, right? Whatever we wrote here, right here, this one. This is also a this is also considered nuclide notation. But for radiation, this is the one that we have. Do you see this in school before? This particular one?
Yeah,
Therefore, this is what we
yeah.
need to know. Okay, so that is point C. And what exactly is nuclide? Is basically we define as an atom with a specific number of proton and neutron. So it's basically just an atom only, nothing much. Okay, can? Okay, point C.
Okay.
Okay, next, let's talk about nuclear decay. So over here, it says that it's a random and spontaneous process. So these 2 points here is important. Just know that it's spontaneous and random. Okay, what is the meaning of spontaneous? Spontaneous means it is not triggered by external factors. Okay, what do we mean by this? Okay, this means that you don't need to trigger by, let's say, suddenly the temperature high enough, then this thing happen, or the temperature low enough, then this particular thing happen. So it doesn't need anything to trigger it. It will just, if it wants to happen, it will happen. So that's called a spontaneous re reaction, so to speak.
Hmm.
When it's random, by random, we means that it is not okay, we are unable to tell when the decay will happen. So again, back to the point, what is a decay? In simple terms, what I can tell you, decay is that in a nuclear decay, because it's nucleus, okay, we say that an unstable nucleus losing energy. And how does it lose? How does it lose energy? It loses energy by losing either particles or either you lose particles or you lose what should I use? Okay, lose gamma rays. Gamma rays is the one that is that you have seen in the electromagnetic spectrum, that gamma rays. So basically a decay is just a nucleus losing this energy. And how does it lose energy? It loses energy by either giving out particles or giving out gamma rays. Okay, but again, specifically how it's happening, not that important. Okay, then so far, all right. Something about the decay. You got any questions about the decay?
Uh,
It's like what are they
Wait,
giving out all this?
it's like the nuclear decay is like my teacher say it's like by half or something, right?
You're talking about half-life, right?
Oh, that's half-life, right? Yeah.
Mm. Okay, so
Right.
if I put it in a pictorial form, okay, so nuclear decay, a very simple term is I got a nucleus,
Mm.
okay, and this is unstable. So after the decay, uh, you can form a few things. So um, I'll just put it as something like it forms a new nucleus. Okay, whatever the new nucleus is, you don't need to know. Okay, it forms a new nucleus and it gives up. Just now we say that it lose energy, right? So energy is given up. And you will give out either particles or you will give out gamma rays plus energy given off. This is nuclear decay, where a nucleus breaks down and it gives out its energy, and in the process it gives out particles and or all gamma rays. Make sense so far?
Yeah.
What are the particles? There are two types of particles that can be given off. It is something called alpha particles, or it can be in the form of beta particles. Okay, what are alpha particles and beta particles? Alpha particles is basically the helium nucleus. Beta particle is basically an electron. And gamma rays is just gamma rays. So when a nucleus undergo decay, it will give up a new nucleus. It will give up energy and it will give up either one of the three things over there or two of the three things over there or all three things over there. Again, that's why when we say that the reaction is random, we wouldn't know. So all
Mm.
you need to understand is these are the possibilities. And in syllabus, right, we need to know exactly what the alpha beta particles are. But this is generally what I can tell you roughly is a nuclear decay process. This process okay so far?
Yeah. Wait,
And
so like when they decay, it can either be alpha or beta.
can be one of the three, can be two
Oh,
of the three, or can be all three also.
oh, okay.
So exactly how I like chemistry equation. Chemistry equation quite standard.
Mm.
Magnesium plus HCl must give you magnesium chloride hydrogen. So this is not spontaneous. This is like standard. You expect this to be like that. But this one cannot tell.
Mm.
Okay,
Okay.
so that is basically nuclear decay. Okay, so that's our point D. Point E, it
Mm.
shows the understanding of the nature of all these things, the ionizing effect, penetrating effect, and penetrating effect, ionizing effect. Okay, so let's do a table here. The phrase they use is alpha beta. So we have alpha particles, also look like this. We have beta particles, and we have gamma rays. So essentially, what are they? So what we want to see here is that alpha particles is the one that is basically a helium nucleus. This is an electron. And gamma rays, because it's a nucleus, right? Nucleus, that's why this guy here is actually positively charged. Because it's a nucleus, nucleus only got P and N in it. And the P is positive, the N is neutral. So basically, this is a positively charged particle. And beta is electron, this is minus. And then for gamma rays, this is just an electromagnetic spectrum, part of the electromagnetic spectrum. Then the other 2 points that are stated in the syllabus is ionization, and the other one is penetrative power. Okay. So in terms of what do you understand by the word ionizing ability?
Is it the chemistry like ionic?
Yeah, form ions lah.
Yeah.
Okay, ionizing ability. So each of the particles, this one is very high ionizing ability, which means that alpha particles can make other particles turn into ion.
Mm.
And then for negative particle, electron, this one is medium strength, and this one is very low ionizing ability. So which means very low doesn't mean don't have, it's just that it doesn't ionize or change substances into ions very easily. So high ionization means that they can ionize particles easily, that's all. Okay, can penetrative ability. This one very low. Again, it's medium. And this one is very high penetrative ability. So very low penetrative ability is, this one is easily absorbed, or they can be easily blocked by a thin piece of either paper, aluminum, or even the human skin. For beta particles, they are absorbed by a few mm of aluminum. Okay, then the last one, gamma, they are being absorbed by a few centimeters of lead metal or very thick concrete. Is this okay?
Yeah.
Okay, I'll show you roughly one of the diagrams that is very commonly used. Make sense?
Mm.
Okay, I'll leave this here first. You take a look at all the nature. This one, the nature is specifically mentioned in syllabus, and ionizing and penetrative ability also mentioned in syllabus. So you look through this table, uh, and then familiarize with it. Then once you're ready, I'll continue. Yeah. Okay, so background radiation, it refers to okay, radiation in an environment where there is no radioactive source introduced. So without a deliberate uh, addition of uh, radioactive source, you still have radiation. So where do you think you can find them?
Uh,
Or rather, why does it even occur? Okay, normally we have two of them, natural sources. Okay, natural sources, example, like rocks, like the sun ray, like even some gases in the air, and maybe things like generate any kind of rocks, and sometimes even food and drinks, they might also have small amount of it.
mm,
Artificial sources, that means are non-natural. Artificial sources include things like when they're doing X-ray machines. This one will also introduce radiation. And then things like now we say rocks, so building materials, building materials like example cement, concrete, all these have radiation. And
mm,
maybe also those are power station, especially the nuclear power station, or even things like your handphone. Okay, all these are, if you use the device to test, you'll probably see all these sort of radiation occurring, especially Singapore, because when we have a hot sun and we are basically concrete forest, we have actually quite a high level of background radiation. Is it okay?
mm. Yeah.
Then so this one is the part on understanding background. Okay, then the last two parts is application and half-life. Okay, what do you understand by half-life? What's your understanding?
Is the particles decay, right?
Mm, is by definition, is the time taken. Okay, for half the nucleus, to decay. So what this means is that the number of so-called radioactive particles or the amount of radioactive activity will keep like dropping by half, keep halving over the same amount of time. So we have something called count rate. Okay, this count rate actually measures, right, the number of decay per unit time. So if you have a lot of particles in the nucleus, a lot of radioactive particles, then your count rate will be very high because if it's not, if there's a lot of particles and they are not stable, they will keep breaking down. So you compare like every 1 minute, right? A nucleus that has 10 billion 10 billion particles in it. This substance that have 10 billion particles that are radioactive. Okay, they break down every minute. Those particles, when they break down every minute, versus another sample with only 5,000 radioactive particles every 1 minute. Which one do you think will have more decay every minute? Is it the one with the 10 billion one or the one with the 5,000 particles?
10 million.
Yeah, actually, yeah, because the more particles you have, the more radiation you will have over the same period of time. Makes sense, right?
Mm.
So to quantify this, we use the term that we use is a count rate. The count rate tells you how much decay is happening at that period
Mm.
of time. So together with half-life, right, this thing allows you uh, to determine certain information. So half-life is the time taken, right, for the particles. Either you can understand it as the number of radioactive particles, or you can understand by the count rates, which is the amount of decay that happens, okay, to drop by half. That is this timing is called uh, half-life. So for example, let's say at the starting point, at the starting before any decay has happened, when you measure the level of radiation, the level of radiation, let's say, has a count rate of, let's say, 10,000. Sorry, let's put 8,000, then the number easier. Okay, let's say 8,000. This object here, okay, this radioactive substance has a half-life of, let's say, 2 hours. So this means that when 2 hours have passed, right, the nucleus will have decayed by half. The existing nucleus will have decayed by half. The amount of decay measured every minute will have dropped by half. Everything will drop by half in 2 hours time. So when you have 8,000, it drops to 4,000 when you have 2 hours pass. And then when the next 2 hours has gone by, the existing nucleus will again drop by half. Okay, it's not 8,000 drop to 4,000, 4,000 drop to zero. 没有啦。The more you have,
Mm,
the faster you drop 啦。So the less you have, the less you drop. But it's always half of the existing one. So
mm,
from 4K in 4 hours time, another 2 hours have passed, you will have dropped to 2,000. Then we have another point here. Okay, same thing, 3 hour, another block has gone by, it will drop to 1,000. And then another 2 hour block, it drops to 500. So you can see the half-life diagram will look
mm.
like this. I think you have seen this before, right?
Yeah.
So that's the meaning of half-life. Simple.
Mm.
Okay, anything you want to check for regards to how you look at count rates, how you look at half-life?
Wait, might just say like the end of the graph, right, is not like
You won't touch on
accurate. Yeah,
because anything is because it doesn't go away totally, ma. It's always
mm,
divided by two, ma. No matter how
yeah.
small is it, you'll keep divide by two. Because from
Oh,
500, you go
so
to 250, 125, 62.5,
mm,
31.25, 15 point something, 7, 3 point something, 1 point something, 0 point something. Yes, it will decay to such a point that the radiation effect is not significant, but it will never, never, never go to zero.
mm.
So for
Okay,
the
so
x-axis,
like
okay,
so when I draw the graph, then it
don't touch.
doesn't like go all the straight all the way down, right?
No,
It will
just draw like what we did here, horizontal will do.
right.
Okay.
Okay.
Okay, before I touch on the application, the users, and the hazards, okay, can you run through all the points here again? Okay, whatever screen that you see here, you just check it one more time. Okay, I will screw up, but make sure all the syllabus points are all right. You run through everything first. The thing that's really new, I would say, is the nuclide notation.
Mm, I think okay.
Nuclear decay, all
Yeah.
right.
Yeah.
Alpha, beta, gamma, okay.
Mm,
Background and half-life, definition, idea, and types.
yeah.
Half-life calculation.
I think the half-life calculation are quite okay.
Okay, can.
Mm,
So, okay, you look at the syllabus description, not the one that I wrote, it's the actual syllabus from A to G. Uh, you understand the points in the syllabus? Then okay,
yeah.
then all right, let's go to users and the effects. So users wise, did your teacher go to very specific? What's the alpha particle used for, beta particle used for all this?
I think have.
Alpha, okay.
Yeah.
So let's look at gamma first. Gamma is something that we have done before in EM spectrum. Under EM spectrum, Do you remember what is gamma rays used for?
Mm. Yeah,
What?
gamma rays is the treat cancer one, right?
Correct. The treat cancer, sterilize, medical equipment, all those things are correct.
Mm.
So let's work not here. Team users. So for gamma, as you mentioned, it's used to treat cancer. Okay, how does it do? It basically destroy tumors. And normally they have very, very short half-life. Okay, the reason why you want short half-life so that it quickly decay away and does not stay in the body for long. Make sense, right?
嗯
那种 super high half-life, then it decays slowly, right? Then the radiation in the body end up more issues also. Right? Then we also use to sterilize medical equipment. And the one that is used to sterilize, normally they have a long half-life. Okay, why do you want to do that? So that no need to so-called replace frequently. So we use long half-life type of gamma radiation for this sterilization. But anything that's injected to the body, we use shorter half-life so that they can totally go away from the particles.
嗯
Can I? Okay. Alpha particles, it is because of its ionizing ability. Okay, it's very, very strong ionizing ability. This is normally used in smoke detector.
嗯
Did your teacher explain to you how this thing works? Or just mention only?
which one?
How the ionizing ability works. Like the actual thing is the alpha particles when um, they can ionize because of their high ionizing ability, they can ionize atoms. And then when they ionize atoms, they become charge carrier, then got currents really. So when the smoke enter, uh, when the s- when the smoke, so under normal circumstances, because of their ionizing ability, the currents will flow in the detector because they ionize the atoms. Then the atoms, when they are ionized, they become ions. Then we
嗯
produce a current. So this current flow will be there all the time. Then when the smoke, right, smoke will absorb the alpha particles. So when they absorb the alpha particles, then they stop ionizing the atoms already, right? Because initially we say that they the alpha particles, they ionize the atom. And then when they ionize the atom, there will be a electric current form. Okay, when there's smoke, smoke will absorb the alpha particle. And then because of this, then no more or less, so ionization will occur. And when you have less ionization occur, because just now we said that when they ionize, there's an electric current. So now the electric current will be disrupted. You agree? Under no smoke condition, the alpha will ionize the atom. The atoms will, when they ionize, they allow current to flow. Then if you have smoke particles coming in, they absorb away the radiation, the alpha particles. Then no more ionization, then the current flow will disrupt. So because of this, the disruption of the current will turn on the alarm. Then you'll ring off. So that's how it is used as a smoke detector. Okay. To digest a bit first. Once ready, I'll go through with you the industrial use for beta and gamma rays. You can use to determine thickness. Of material. This one normally is beta or gamma. So the idea is something like this. So let's say I have a sheet of metal. See over here, I have a radioactive nucleus. And this nucleus can either give out gamma or let's say beta. Then over here, I have a detector. So because the material will absorb the radiation, so let's say under normal circumstances, the count rate, let's say is 100. So whatever radiation that goes through, blocked by this, and then received by the detector, if the thickness is correct, the count rate, let's say, is 100. Okay, now what happens when you receive a count rate of, let's say, 60? And what happens if you receive a count rate of 143? What does that mean in terms of the thickness of the material? Remember, the radioactive substance is passing through the material. So if your count rate drops to suddenly 60, what does it tell you about the thickness? The piece of material that's being tested now, is it too thick or too thin if you register 60? Remember, if when the radioactive particle pass through, too thick, the more particle being absorbed, right? Then the value will drop. Make sense?
Yeah.
The amount that can pass through become lesser,被block. So you can see is the thicker the material, the more blocking you'll get. So at 60, most likely is too thick. Then 143.
143 is too thin.
Too thin because by right normal should only have 100. So if you allow more particles to go through, that means most likely the material is too thin. So from here, you can roughly estimate that this thing here, this part of the material is too thick. And when the value drops too much, increases by too much, it should be too thin. Understand? So this one we can use either alpha or beta. Sorry, we will use beta or gamma rays to do it. Why do you think this one cannot use alpha? For determining thickness.
Alpha
not
cannot
suitable.
go through, right?
Why cannot go through?
Because the penetration very low.
Correct. is easily blocked by paper. So even paper can block it, you cannot do anything. So no matter what, right, if you use beta alpha particles, because of its low penetrative ability, correct? Your detector cannot detect anything. Then waste time. Yeah.
Yeah.
Okay, so the user's comfortable. Basically these few lah. For the alpha smoke detector, then for beta and gamma thickness testing. This is for the industrial side. The medical side is normally gamma radiation for the surgical equipment and for treatment in cancer.
Mm.
Okay, and the last one is hazards. Okay, so hazards, the usual thing is when you get exposed to radiation, okay, it can damage human cells or tissues. Why is it able to do this kind of damage, right? Because they can damage tumor is cells also, right? So they can also do the same thing to this. So I think for this case, the reason why this thing can be damaged is due to ionizing radiation. When the radiation is very ionizing, aka high ionizing power, they are normally the ones that will cause damage. That's why alpha particles cannot be used for medical because they are so so what do you mean? They are like very high ionizing. So if you, I mean, first of all, the radiation sucks. It can be blocked by the skin, so it doesn't work really. But even if it
Mm.
works, you penetrate it, you're going and full scale destruction of everything because it's so highly ionizing. That's why gamma is very good for this kind of purposes because it is very it can target the tumor area, and then because it is not so ionizing, it doesn't cause major destruction to the other healthy cells. Whereas if alpha particles can enter, then you'll kind of go full scale destruction of everything because it's so ionizing. So you kill the tumor cells, you also kill everything else. So that's why it is good to use gamma for cancer treatment. Okay, due to the fact that when radiation are ionizing, they can cause damage to human cells.
Mm.
Okay, okay, and the last
Mm.
part is how to safety. Okay, when handling this, number one, okay, storage of the material. They should be in a shielded container. And this shielded container ideally use their lead line. So if you want to carry around radioactive substances, make sure it's in a box that has the walls of the box, right, being the lead metal. Then when handling all this, you should use lead line gloves, clothing, and so-called clothing or suits that has layers of lead metal around it. Okay, then common sense is limit exposure time. Okay, you can also increase the distance between the person and the source. How do we do it? You can use things like tongs, or you can use anything that avoid Basically is to avoid direct human contact. Okay, for safety, check hazards and safety.
Yeah.
So if that's our last bullet, that's all your syllabus. Any question you want to check with me, especially from the stuff that you've seen in school?
I think mostly quite clear already.
Yeah, okay, can.
Because now we're doing the